Hello, I am Fabian Perez, and in this video I will present our paper Beyond Appearances Material Segmentation with Embedded Spectral Information from RGB-D Imagery. This is a joint work with Hubert Rueda Chacón, done at the Universidad Industrial de Santander. The task of material segmentation involves predicting a dense map of material labels. For instance, in this image of a motorcycle, we can distinguish between different materials like metal, plastic, asphalt, etc. Unlike semantic segmentation, which only labels entire objects, material segmentation provides detailed information about each part, enhancing the details of a scene. Material segmentation has a wide range of applications. In autonomous driving, it helps vehicles differentiate road materials. For real-world simulation, it enhances the realism. In robot navigation, it helps to understand the scene and make decisions. And there, the depth estimation is very important. Depth images provides information about the distance of objects within a scene. Using advanced neural networks, we can now generate depth data from a standard RGB image and also calculate point clouds. This capability is particularly important for adding depth to datasets that initially lack this dimension. In this work, we focus on utilizing RGBD images acquired with LiDAR, a technology now integrated into consumer devices. The classical approach to material segmentation primarily uses RGB images. However, this method has limitations due to metamerism, where different materials can appear identical under certain lighting conditions. For example, these chest patterns shown here look the same but are made from different materials, or the case in materials like plastic, where can exhibit a wide range of appearances, complicating accurate segmentation. To overcome these limitations, we introduce spectral information. Each material exhibits a representative spectral signature, which enables discrimination based on inherent properties. As shown here, different materials like brick, stone, wood, and marble have distinct spectral signatures. Building on this, we propose a deep learning framework that bridges the gap between high-fidelity material segmentation and the practical constraints of data acquisition. We start with RGB and dead images. These images enter an encoder-decoder architecture where they are transformed into spectral reconstructed features. These features are then fed into our proposed spectral feature mapper. The SVM processes these features and outputs logics which after passing throughout a softmax layer result in the final segmentation map. This entire process is trained using a segmentation and a spectral reconstruction loss that integrates spectral information into the network. The losses are combined in a weighted sum, where it's crucial to note that the weight of the segmentation loss is greater than the reconstruction loss to ensure convergence. Let's delve into the role of the spectral feature mapper model. Imagine a scenario where the reconstructed features are identical to the spectral cube, which is highly unlikely but useful for understanding. In this model, we have a learnable parameter matrix of size C times B, where C represents the number of classes and B the number of spectral bands. To illustrate, consider a pixel from the spectral cube along with its bands. The spectral angles are calculated by comparing the spectral signatures to gauge similarity. Smaller angles indicate higher similarity. This comparison is done pixel by pixel, but we propose to calculate it in an efficient and tensorial way with this formula for the entire image. From this, we derive a cube of dimension h times w times c that passes throughout a softmax function, resulting in a probability cube with a class mask prediction for each class. It's critical to note the use of a negative sign in the calculations, ensuring that smaller angles, which indicate higher similarity, result in a higher probability post-softmax. Our framework facilitates material segmentation using just mobile devices, bypassing the need for spectral data. Captured images from everyday mobile devices are processed throughout our encoder-decoder system and the SVM layer to achieve precise material segmentation. The segmented outputs are then projected onto XYZ coordinates, creating detailed point clouds that enhances spatial understanding. Our framework was evaluated on the libHCI dataset. To optimize the segmentation and integration of spectral features, we utilized focal loss for segmentation and mean square error for spectral reconstruction. This loss helped target a specific challenge in our training process. The results demonstrate a clear improvement over traditional FSCN and UNet models. Our approach significantly enhances material segmentation accuracy and seamlessly integrated with point cloud generation. For example, here we can observe that our method successfully predicts the correct classes despite the challenging appearances. For our real-world experiments, we used an iPad Pro, taking advantage of its capability to capture high-quality RGB images and depth information through its LiDAR scanner. Also, we used the Apple ARKit SDK to efficiently acquire the necessary RGB-D data. These images were taken by us in real-world conditions, without any labels. Here we present the qualitative results. As we can see, the model successfully generalizes and accurately segments different materials. In summary, our spectral feature mapper model significantly enhances material segmentation by embedding spectral characteristics into encoder-decoder architectures. This approach has led to marked improvements over traditional RGB methods, leveraging spectral data without the need for specialist sensors. Additionally, our framework validation with consumer devices like the iPad Pro demonstrated its potential for widespread adoption and diverse applications. Please check our paper and our code for more details.